All right. Well, thanks everybody, and thanks Brian for organizing this. So what I'm going to do is just to give a very quick overview of some of the stuff my group has been working on, and most results I'm going to show are sort of newish, but just for some continuation and background, I'll also talk about some studies that we have done in the past, which I think maybe some of you have heard about this. So please bear with me on this. So overall, my group is interested in this nexus between air pollution, climate change, and human health, and we're sort of specifically focusing on both on the impact side, which are sort of climate influences on air pollution, extreme weather ish, and then some of the solutions. So that involves some policy evaluation, which I'm not going to talk too much today. So right now we're mostly focusing on the three underlying questions. Number one is to think from a climate impact perspective, what are the climate change influences on air quality, and through this channel, its influence on human health. Number two, this is sort of zooming in really on wildfire smoke as an air pollution source, and this is particularly relevant in the US, but also other parts of the world that many of the traditional air pollution sources have really been going down, and wildfire is this source that has been increasing, and this is becoming sort of almost a number one air pollution sources in many parts of the US. And then number three is on the policy or the solution perspective that we're trying to understand the effects of energy and climate policies on air pollutant emissions, air quality, and human health. So I'm not going to talk too much about this today, but so I'm mostly just focusing on the first two. So I'm going to show this slide just for a motivation. So this is not our work. But this is from an earlier paper in Nature Climate Change, but the results are sort of still there. So like there hasn't been much change in the conclusion. So what I'm showing here, what you're looking at, this is across different climate models, right? So on the x-axis, so GFDL, GISS model, all that. The changes in the mortality related to fine particulate matter, so PM2.5. And this is sort of holding emission constant, right? So just to change the climate. So compare RCP 8.5, 2100 to, I think, the historical period. So what we see here is just the different climate models really have a huge disagreement with each other in terms of what are the projected changes in PM2.5 under a future climate. And this is really speak to that there are a lot of mechanisms involved in this climate pollution linkages. So those are including both the natural emissions like wildfire, dust emissions, the circulation patterns, or the broader atmospheric chemistry, atmospheric transport patterns, and then some of the understudy patterns, including how climate is influencing the human sector emissions, like how people are using energy, things like that. So this has always been a great motivation for us to look at this, that there are a lot of uncertainties still in the space. And what we try to do is sort of break this into different mechanisms. So like we have studies directly looking at wildfire, like climate influences on wildfire and its contribution to PM. And we have other things sort of going on for energy, etc. But this is sort of a motivation that, I mean, this is obviously a really important topic, but we have a lot of uncertainty in this space. So I'm going to talk a little bit on wildfire specifically because I already mentioned that this is now the sort of the one of the really the most important air pollution sources in the US, and this is certainly the one that is fastest growing. So there are some of our effort has been looking at how do we really model wildfire smoke influences on air pollution. So broadly speaking, there are these two approaches. One is the more traditional atmospheric chemistry air quality model simulation that we do two sets of simulation, one without wildfire and one with wildfire, and then we take the differences across the model simulations, and that's our understanding of wildfire. This has been really challenging for wildfire smoke compared to some other known sources like power plants, because it's really difficult to estimate the amount of emissions being emitted from wildfire. There are also other parameters. One of the most important one is the injection height, which is basically at the vertical level where you put emissions into the atmosphere. Of course, when it's lower, when injection height is lower, sort of the impact is more on the surface. But when it's higher, it's more sort of it has a longer range transport. This is also something that we don't quite understand very well in the model world. So alternatively, there is another set of approach that we have been using quite a lot is taking this data-driven technique. So this is directly sort of without really trying to understand what's going on or without improving the wildfire process, but really treat this as a data science kind of problem that we are trying to leverage a set of information, satellite information, meteorological information, fire information to try to predict what are the increases in surface pollution during wildfire smoke episodes. And this has been shown to be, so we have some earlier work on this, that this has been shown to be really useful information for instance, people doing public health because they want this high resolution information.
In the upper panel,
yeah,
I can't make out what the scale is on the right.
Yeah, so this is I believe this is a monthly simulation. So you are talking about that one.
Yeah, but the color bar, what is
the color bar, yeah.
What does it represent?
So this is, I think, a monthly simulation. This is one, maybe September 2020. That was when you have this big wildfire in Northern California, Oregon. This is about 10 microgram. This is 30, the highest bin is about 30 microgram per cubic meter. So the monthly concentration. And then, so what you look at is, of course, without wildfire, this is in the range of 5 to 8 in California, or even below that in Northern California, Oregon, but it goes up dramatically when you consider wildfire.
Got it.
Yeah. So one of the interests is really to think about what's the what are the intercomparison between the different approaches, right? So there is the broadly speaking, the modeling approach, and then there's the machine learning approach. Right now, it's really like they're a very isolated community in some sense. Like the public health people, they really like the machine learning approach because it often gives you the sort of the higher data quality and it's easier to run. They don't need to set up the computing model, obviously. But the atmospheric chemistry community, I think, is more still. We do a lot of the CMAC or the kind of model simulation, and then of course there is some effort trying to combine them together, but not as much, I would argue. So this is a earlier paper that we did this evaluation of the 3 approaches. So these are the 2 models, GeoSchem and CMAC, and the ML, the blue one is the machine learning approach. And we do this sort of by comparing to the surface measurements during the wildfire smoke on PM 2.5. And what you see on this map is each of the colors shows which method performs the best across the 3 methods. So basically what's seen here is across the Western US, again, this is in 2020, so the high smoke year, machine learning really performs the best or capturing the surface observation the best in those high fire regions. But like when you are looking sort of beyond Western US in the Eastern US, right? So those are, they still have some fire. Some of them are transported fire, but that's where you really see that the models seem to give you the best agreement with surface measurement compared to machine learning. So that has been a puzzle to us in 2020. And now Xinyi, a PhD student in my group, is sort of expanding on this work that we're looking at a longer set of simulations. So from 2006 to 2021, comparing CMAC and machine learning. One of the objective of trying to understand this is so what, right? So if their simulations are different, so what? So one of the thing we are interested in is like how do the different estimates link to different house impacts, right? So if you use CMAC smoke estimates versus the machine learning smoke estimates, like, and if you conduct the same set of epidemiological studies or house impact studies, do you have similar different results? And it turns out that you can have some different results. So this is looking at how mortality rate change across the different level of wildfire smoke. So there are some agreement, but there are also some differences in terms of the different approaches. So that's another way to say that from the house impacts assessment perspective, like we do really care about like which method is sort of more accurate, and that helps improve that. This is sort of, again, as I mentioned, like we are doing a lot of this machine learning type of work. So this is work I contributed to. So we are continuously sort of updating this kind of data set. So this is generating the smoke PM2.5 level that is specifically contributed to wildfire. And you can very clearly see that sort of in the last 5 years, wildfire smoke PM has really, wildfire smoke really contributed a very high level of PM2.5, and you can sort of see 2023, for instance, this is kind of going crazy. That's the year that the Canadian wildfire smoke going all the way to covering eastern US. So linking this back to climate change, so this is a paper published in Nature last year that we built this model that's sort of trying to understand what are the level of wildfire smoke PM2.5 and its related mortality under future climate scenarios. And we're doing this until the year 2050. So it's not looking good. Under future climate scenarios that we're projecting to see very high level of wildfire smoke pollution if we don't, and this is sort of the business as usual in land management, all that kind of stuff. So this is not inevitable, right? So we can do better land management or prescribe fire, things like that to reduce this. But if the land management or the fire policies are sort of the same, just with climate change, that higher temperature, drier, few moisture, all that, we're going to see a higher level of wildfire smoke pollution, not just in Western US, but mostly in Western US, but also make it all the way to Eastern US. Another thing is in 2050, there are not that many differences, right? If you look across the different climate scenarios, so this is the SSP1, this is the most optimistic emission scenario, right? Even under that scenario, we're still going to see tons of wildfire smoke in 2050. This is a paper that is forthcoming at PNAS that we sort of take this model and just sort of put this into an economic sort of model. And this is almost laughable right now under the current EPA, but you guys should know that EPA used to care about those kind of stuff. And then one of the metrics they do is the social cost of carbon, which is basically a central piece that they use to evaluate whether climate policy is cost effective or not. So the social cost of carbon is that if we emit 1 ton of CO2 to the atmosphere, what are the additional damage it does to the society? And so this is the benefit of a climate policy, and you compare this to the cost of the policy, right? So one of the contributions we made in this paper is in most of the models that calculate social cost of carbon, wildfire smoke is not in it, right? So most of the previous social cost of carbon model, they talk about temperature-related mortality, agriculture, energy, things like that. So this is just talking about the damages within the US. So now we add wildfire smoke component to this model. And what we find is, at least within the US, wildfire smoke is perhaps one of the really important channels, right? So by incorporating wildfire smoke, it really increases the social cost of carbon in the US. And again, that just talks about that the tools that we use to evaluate policy really underestimate the benefits of carbon emission reductions. The wildfire smoke, of course, contribute a lot of stuff in addition to PM. So this is a study that is sort of using a similar approach that we're looking at its effects on ozone, right? Which is, of course, another important criteria air pollutant. What we find is really interesting is that wildfire, for one, also contributes substantially to ozone. So that's not necessarily surprising. I think the second thing what we find is really surprising is that the wildfire smoke impacts on ozone are pretty weakly correlated with wildfire smoke impacts on PM, right? So they don't always happen together, right? It's not like when you have a day of high PM, you necessarily have a day of high ozone. I mean, that's of course because ozone is a more secondary pollutant that is reacted in the atmosphere, not necessarily directly from the fire emission. And this, again, has very important health implications because if you look at the health literature, almost 90% of the papers are looking at PM2.5. And that's, of course, important, but they are sort of ignoring some of the effects from other pollutants, one of them is ozone. So what we see here is because they don't necessarily overlap, so if you only look at PM, maybe one of the low health risk scale, you used to think it could have very high level of ozone, right? So sort of really talks about this mischaracterization of health risk from well testing. I think I'm running out of time, so I'll just skip all of this to say that the final thing we're working on, this is led by De Yang, another PhD student here. So we're looking at sort of this assessing this temperature PM sensitivities. So I think I showed some of the data before for US, but De Yang is expanding this work across to about, I think, 50 countries that we have reliable PM 2.5 measurement. So there are, I mean, it's definitely not across the world. Many of the part of the world still under monitor, but we have good data in Asia, Europe, US, and some in South America. And what he finds in a preliminary analysis is that they tend to have very different sort of relationship between temperature and PM. So like, for instance, US and China is what we call sort of this J shape, right? So under the lower temperature, the PM doesn't really change much, but it really take off when the temperature is very high. And in many countries of Europe, for instance, has sort of this U shape, where both the extreme low temperature contribute to increased PM, and then the extreme high temperature contribute to increased PM. And then this is, our hypothesis is this is related to sort of their winter heating energy, that being mostly wood and oil that contribute a lot. Yeah. All right. Thank you.
Any questions? When you were talking about the climate projections of smoke, how do the models actually like compute that? Are they using like ignition probabilities? Do they count human ignitions and like natural emissions? And then how do they? I mean, there's a couple of models between them.
Yeah, definitely. Yeah. So the results I show, they are still sort of on top of our earlier data-driven kind of approach, right? So what they do is, so there are sort of two processes. One is we try to learn this relationship of how does historical wildfire emissions change as a result of moisture, temperature, wind speed, things like that. So the assumption there is sort of you're assuming that the ignition will remain constant in future. But then there is another step on top of that, which is, I mean, we know that it's important to consider this feedback, right? So like when you have more fire, you burn down more stuff, and that reduce the fuel available for future fire. So we have a sort of a correction step in there, but then it's sort of, it's somewhat important, but it's not. It definitely cannot reverse the trend anyway. So that's the approach we use. I mean, broadly, the literature has been, people couple the vegetation model with climate model, and then there's often a fire module in it, and then they have some heuristic formula for ignition risk. So those kind of models turns to be really not performing very well when you compare them with the historical with the historical data. I think the reason people are still trying to figure out.
So instead, you use the data to make the connections between variables. And
so that's the method we use. Yeah.
So what you're saying is that once all the forests burn down, there won't be any more wildfire smoke.
Yes, that's right. There is, but according to our model, there are still tons of forests to be burned down in the U.S.
Well, I'm going to do one online first because I forgot them last time, and then I'll get to you, Bob. Edmund has a question. Why are the smoke projections seemingly not quite sensitive to the projected pathway?
Yeah, great question, Edmund. So I think the short answer is that we stopped the projection at 2050, and then of course when you look at the model simulations in 2050 across the three warming scenarios, they don't differ that much, even in their projected temperature, soil moisture, those kind of stuff. So if we run this out to 2100, the differences are much larger. That the SSP1 is projecting much lower smoke. But then I think we feel a little nervous projecting so long ahead, just purely based on a sort of the statistical relationship, because maybe we're extrapolating too much. So I feel like 2050 we're sort of okay with.
Do one more, Bob.
I'm wondering how you translate exposure to death.
Yeah.
That is, what's the time integration of that? How do you look to the future in projecting deaths, or is it some death that year, or how do you derive the death rate?
Yeah, the great question. So what we did for the deaths is we sort of the scale is at the basically the year it's sort of at the year level, right? So we have the county level mortality data, and we link this mortality to the level of wildfire smoke they exposed to the same year and the year after. So sort of we consider some of this lag effect. In fact, we actually see increased mortality after 3 years after exposed to smoke, but that's a little bit. I mean, the confidence interval is sort of getting really large when you look a little further years, or sort of as a conservative estimate, we stop at year 0 and year 1, and then for future, so there are the some of the projections in the baseline mortality rate, basically. So in the future, one thing that really important is the aging of the society. That the baseline mortality rate for the elderly population, of course, is higher. So that also contributes quite a lot to the future wildfire smoke deaths. So not just more wildfire smoke, but also the changes in demographics.
Interesting, complicated. Great, let's thank Minghao again.
Thanks.